Jupiter unveiled. What Juno found beneath the clouds. The deep atmosphere. NASA Juno spacecraft has fundamentally transformed our understanding of Jupiter atmosphere by revealing that the planet-iconic jet streams and storm systems extend far deeper than anyone predicted for decades. Astronomers observed the magnificent banded clouds racing across Jupiter's surface at velocities exceeding 400 km per hour, but the depth of these features remained a mystery. The prevailing assumption was that these atmospheric phenomena were relatively shallow effects confined to the upper few hundred kilometers of the atmosphere. Juno gravity measurements and microwave radiometer data have shattered this assumption. The jet streams that create Jupiter distinctive belts and zones penetrate approximately 3,000 kilometers below the visible cloud tops. This is roughly 3% of Jupiter radius and represents a mass equivalent to about 3 times that of Earth. The jets are powered by the planet's internal heat, which radiates more energy into space than Jupiter receives from the Sun. This internal heat drives convection currents that organize into stable east-west flow patterns. The persistence and depth of these jets indicate that Jupiter's atmosphere is not a thin veneer but an integral component of the planet dynamic system. The Great Red Spot is perhaps the most iconic feature in the solar system. This anticyclonic storm has raged for at least 400 years since astronomer Giovanni Cassini first documented it in the 1600s. From afar, it appears as a beautiful swirling oval roughly 16,000 kilometers wide, large enough to swallow Earth whole. Juno has revealed that this storm extends vertically for about 300 to 500 kilometers, making it far deeper than expected, but still relatively shallow compared to the overall atmospheric depth. The storm routes are anchored in layers where water clouds form, and the temperature and pressure conditions allow complex chemistry. What makes the Great Red Spot so enduring is still not entirely understood, but Juno data suggest it draws energy from smaller storms that merge into it, and from the vertical temperature gradients within Jupiter's atmosphere. Unlike hurricanes on Earth, which dissipate when they lose contact with warm ocean water, the Great Red Spot feeds on Jupiter's internal heat and atmospheric turbulence, ensuring its longevity. The storm drifts slowly westward relative to the planet's magnetic field and occasionally interacts with other vortices, sometimes absorbing them and sometimes being perturbed by them. The core paradox. Before Juno arrived at Jupiter in 2016, the dominant model of the planet interior was relatively straightforward. A dense rocky core, perhaps 10 to 20 times the mass of Earth, sat at the center, surrounded by a thick shell of metallic hydrogen where pressures exceed 1 million Earth atmospheres, and hydrogen behaves like a liquid metal. Above that was a layer of molecular hydrogen and helium transitioning smoothly into the atmosphere. This model was elegant and fit well with theories of planetary formation, where solid cores accrete gas from the surrounding protoplanetary disk. Juno gravity mapping has revealed a far stranger reality. Jupiter core is not a compact solid object, but instead appears to be diluted or fuzzy. Heavy elements such as iron, nickel, and rock are mixed throughout a broad region extending outward from the center, possibly reaching halfway to the planet's surface. The core is not sharply defined, but instead gradually blends into the surrounding hydrogen and helium envelope. This discovery poses profound questions about how Jupiter formed. One hypothesis is that early in Jupiter history, a massive collision with a planetary embryo disrupted the core, sending heavy material outward into the envelope. This would have been an event of staggering violence, a Mars-sized or even larger object slamming into the young gas giant at tens of kilometers per second. The impact energy would have been sufficient to partially vaporize the core and create turbulent mixing currents that persisted for millions of years. Another possibility is that the core never fully solidified during Jupiter formation. Instead, as the planet rapidly accreted gas, the tremendous heat generated by gravitational compression and the decay of radioactive elements kept the core in a molten or partially molten state, allowing convection to mix heavy elements upward over time. This scenario implies that the core and envelope have been in dynamic exchange throughout Jupiter's entire 4.6 billion year history. A third model suggests that erosion processes driven by the immense pressures and temperatures at depth gradually dissolve the core. Heavy elements could be transported upward by convective currents and redistributed throughout the interior. This ongoing erosion would mean that Jupiter core has been shrinking slowly over billions of years. Regardless of which model is correct, the diluted core fundamentally changes how scientists think about gas giant interiors. It suggests that these planets are far more dynamic and less stratified than previously believed. The boundary between core and envelope is not a sharp transition, but a gradient zone where heavy elements and hydrogen are intimately mixed. Magnetic fields. Jupiter's magnetic field is the strongest of any planet in the solar system, reaching intensities of about 4.3 Gauss at the cloud tops near the equator. This is roughly 10 times stronger than Earth's magnetic field and extends millions of kilometers into space, forming a vast magnetosphere that would appear larger than the Sun if visible from Earth. Charged particles trapped in this magnetosphere create intense radiation belts that pose serious hazards to spacecraft and would be lethal to
protecte humans.
Juno has mapped Jupiter's magnetic field with unprecedented precision, revealing that it is profoundly asymmetric. The northern hemisphere field is significantly stronger and more complex than the southern hemisphere field. This asymmetry is so pronounced that scientists have dubbed one feature the Great Blue Spot, a region of intense magnetic flux concentrated in the northern mid-latitudes. The name echoes the Great Red Spot, but the two phenomena are entirely unrelated. The Great Blue Spot is not visible to the eye but shows up clearly in magnetic field measurements. The lopsided geometry of the magnetic field tells us something fundamental about the interior structure of Jupiter. Magnetic fields and planets are generated by dynamo processes, where electrically conductive fluids move through existing magnetic fields, inducing currents that amplify and sustain the field. In Jupiter, this dynamo operates in the metallic hydrogen layer, where pressures exceed 1 million atmospheres and hydrogen transitions from a molecular insulator to a metallic conductor. The asymmetry suggests that the flow patterns in the metallic hydrogen layer are not simple or uniform. Instead, there may be large-scale convective rolls or jets similar to atmospheric jet streams, but occurring thousands of kilometers below the surface in a liquid metal. These deep flows are influenced by Jupiter's rapid rotation, with a day lasting less than 10 hours. The Coriolis forces generated by this rotation organize the flows into columnar structures aligned with the rotation axis. Another intriguing feature is that the magnetic field appears to be changing over time. Comparing Juno measurements with earlier data from the Voyager and Galileo mission, scientists have detected secular variation in the field strength and geometry. This variation is slow, occurring over decades, but it confirms that Jupiter dynamo is an active evolving system, not a static fossil. The magnetic field also interacts strongly with Jupiter moons, particularly Io, which is the most volcanically active body in the solar system. Io orbits within the intense radiation belts, and its volcanic plumes inject sulfur and oxygen ions into the magnetosphere. These ions are picked up by the rotating magnetic field and accelerated to high energies, creating a torus of plasma that encircles Jupiter. The interaction between the magnetic field and the moons creates spectacular auroras at Jupiter. Poles visible in ultraviolet and infrared wavelengths. Water abundance. Water is a critical tracer of planetary formation and evolution. In the early solar system, water existed as ice beyond the so-called snow line, a boundary where temperatures were low enough for water to condense. The amount of water in Jupiter's atmosphere provides clues about where and how the planet formed. If Jupiter formed beyond the snow line and accreted large amounts of water ice, its atmosphere should be enriched in water relative to the Sun. If it formed closer to the Sun and migrated outward, water might be less abundant. For years, measuring Jupiter water content was frustrating. The Galileo probe, which plunged into the atmosphere in 1995, found surprisingly little water, but it descended into an unusually dry region, a meteorological anomaly that gave a misleading picture. Juno microwave radiometer has the ability to peer deep into the atmosphere, measuring thermal emission from layers far below the clouds. This instrument has provided the first global assessment of water abundance. The data show that water is present in significant quantities throughout the deep atmosphere. The abundance varies with latitude and depth, but overall Jupiter appears to be enriched in water by a factor of about 2 to 4 times the solar value. This enrichment supports the idea that Jupiter formed beyond the snow line, where water ice was plentiful and accreted large quantities of icy material along with gas from the protoplanetary disk. The distribution of water also reveals active meteorological processes. Water vapor is transported vertically by convection and horizontally by jet streams. In some regions, updrafts carry water vapor to high altitudes, where it condenses into clouds of ammonia and water ice. In other regions, downdrafts bring dry air from above, suppressing cloud formation. These convective cells are analogous to thunderstorms on Earth, but operate on vastly larger scales, with individual storms spanning thousands of kilometers. The presence of water also has implications for chemistry. Water reacts with other atmospheric constituents to form ammonia hydrosulfide clouds, and possibly contributes to the formation of complex organic molecules in the upper atmosphere. These processes may be relevant to understanding prebiotic chemistry and the potential for life in other planetary systems. Internal structure and formation. Gravity mapping is one of the most powerful tools for probing planetary interiors by precisely measuring how Jupiter gravity field tugs on Juno as it orbits. Scientists can infer the distribution of mass within the planet. This technique revealed the deep jet streams, the diluted core, and other features that were invisible to remote sensing. The gravity data show that Jupiter interior is not in hydrostatic equilibrium where pressure and gravity are perfectly balanced. Instead, there are density anomalies associated with the deep atmospheric flows and possibly with compositional variations in the envelope. These anomalies are small but measurable, and they provide critical constraints on models of Jupiter structure. One of the most important findings is that the transition from molecular hydrogen to metallic hydrogen occurs at a depth of about 10,000 kilometers below the cloud tops, deeper than some earlier models predicted. This transition is gradual rather than sharp, with hydrogen gradually becoming more conductive as pressure increases. The metallic hydrogen layer extends from this transition zone down to the diluted core region, occupying the majority of Jupiter volume. The gravity data also constrain the total mass of heavy elements in Jupiter, estimated to be between 10 and 50 Earth masses. This is a substantial amount, far more than could be contained in a compact core. The distribution of these heavy elements throughout the envelope suggests that Jupiter interior has been thoroughly mixed either by early violent events or by ongoing convection. Formation models now incorporate these findings. The leading scenario is that Jupiter began as a solid core of rock and ice that grew by accreting material from the protoplanetary disk. Once the core reached a critical mass of about 10 Earth masses, it triggered runaway gas accretion, pulling in hydrogen and helium from the surrounding nebula. This process happened rapidly over a few 100,000 years. The intense heat generated by this rapid accretion may have prevented the core from solidifying or may have caused partial melting and mixing. Another scenario involves pebble accretion, where small centimeter-sized particles drifted inward through the disk and were captured by the growing planet. This process could have been more efficient than traditional planetesimal accretion and may have allowed Jupiter to reach the critical core mass more quickly. Pebble accretion naturally leads to a more diffuse core as the accreted material is deposited over a range of depths. The Juno mission has also provided insights into the abundance of other heavy elements such as nitrogen, carbon, and noble gases. These elements are thought to have been delivered to Jupiter in the form of ices and clathrates, compounds where gas molecules are trapped in ice crystals. The enrichment patterns of these elements relative to the Sun provide additional clues about the temperature and chemistry of the disk at the location where Jupiter formed. Conclusion: Juno has revealed Jupiter as a far more complex and dynamic world than previously imagined. The deep atmosphere, with its powerful jet streams and enduring storms, is intimately connected to the planet's internal heat engine. The diluted core challenges our understanding of planetary formation and suggests a violent or turbulent early history. The asymmetric magnetic field points to complex dynamo processes in the metallic hydrogen layer. The water abundance and distribution provide crucial constraints on where and how Jupiter formed, and the gravity mapping ties all these observations together, revealing a planet where convection, rotation, and composition interact in ways that are still not fully understood. Jupiter remains a world of extremes where pressures exceed millions of Earth atmospheres. Temperatures range from freezing cloud tops to tens of thousands of degrees in the deep interior, and magnetic fields trap radiation at lethal intensities. Yet it is also a laboratory for understanding planetary processes that operate across the galaxy. Every gas giant we discover around other stars is in some sense a variation on the Jovian theme, and the more we learn about Jupiter, the better we can interpret those distant worlds. The Juno mission continues to orbit Jupiter, collecting data that will be analyzed for years to come. Each pass reveals new details about the atmosphere, the magnetic field, and the interior structure. The mission has already transformed our view of the King of Planets, and its legacy will shape planetary science for decades. Future missions may send probes deeper into the atmosphere or deploy seismometers to detect internal vibrations, but Juno has laid the foundation for all that follows. In the end, Jupiter is a reminder of the richness and complexity of the solar system. What appears from a distance as a serene gas giant with beautiful cloud bands is in reality a churning world of deep currents, hidden storms, and an interior structure that defies simple categorization. It is a planet that continues to surprise and challenge us, pushing the boundaries of our knowledge and inspiring new questions about how planets form, evolve, and behave.